Hello everyone. I hope that all of you are fine and enjoying good health. Welcome to another lecture of robotics. In this lecture we shall study about homogeneous transforms, rotation matrices and transformation matrices. In the previous lecture, if you remember, we talked about the kinematics and inverse kinematics of robotic manipulators. We talked about the geometric method to find the kinematics and inverse kinematics. But in reality, there are other methods also. For example, there is also algebraic method for finding kinematics and inverse kinematics. And to use algebraic method, we have to first understand some basic concepts about transformation matrices. So that's why in this lecture we study about these transforms. So if you want further study, I shall refer you this book, and the book is you can study about book number Elements of Robotics, and the chapter number is 16. And this is the first book, and the second book you can study Introduction to Robotics, and chapter is 2. So yeah, these, if you want further details about the topics, you can refer to these two books. Okay, so the first thing is why we need these transformation matrices or rotation matrices. So the first thing is so if you remember from the robotic manipulator, what we have, it has some kind of joints, and then there are some links, and on this link there are also some kind of manipulation device or gripper to manipulate the object. Okay, so in the previous lecture we talked about the using geometric method. We found the inverse kinematics, and kinematics. Using the geometric method. So that's we did in the previous one, but for now we shall use algebraic method, for kinematics. And for algebraic methods, we need to understand the concepts of transformation matrices. Okay, so our goal is to find the position. So this is a robotic manipulator, and so we have joint 1 here, and then joint 2, and this is link 1, then we have link 2, and this is we have gripper here to pick and place the devices. So to find the final position, what we are interested in, position and orientation of this gripper. So we are interested in the position and orientation of this gripper. So that's why we need some kind of transformation matrices. We have some here references frames here also, and again here also we have. So what we do, we try to transform one reference frame to another one. Let's say this is a frame A, or call it frame 1. This is XA and YA. This is YB and this is XB. This is YC and this is XC. So to find the final position and orientation of your gripper, what we need to do, we need to find the position and orientation of this the frame attached to this gripper, which is the frame name is C, or you can also call it a reference coordinate system, sorry, body coordinate system. And what we do, to find the position and orientation of this frame, we calculate it with respect to this frame, which is B, frame B, and then we calculate the position and orientation of frame B with respect to frame A, and that's how we transform the position and orientation of the gripper in this C frame to frame A, which is our reference frame. So for that purpose we need transformation matrices or some kind of rotation matrices, and so that's why we are studying this. Okay, so one important thing is reference frame or coordinate system. Of frame. So we can have a 2D planar, or we can call it planar frame, in which we have two coordinates here. Both of these coordinates are orthogonal, means they're at 90 degrees. Okay, this is x-axis, this is y-axis, and here we have origin. And let's name this frame, let's say frame A, and we here put a subscript of call it XA and YA. So this is important. We need some kind of frame first for define the position of any object. We can also use a 3D frame. So in this case we have three-dimensional, 3 axes, and all these 3 axes are orthogonal to each other, means they are at 90 degrees. We have x-axis, let's call this frame B. Here we have origin, and this is x of B, this is y of B, and then we have Z. So this is a 3D frame, and here we have two-dimensional frame. So you can also call it 2D. So once we have the frame, then it's easier to locate any point or anything, any object, any rigid body in this frame. So now we shall learn about how to find the position of any point or a rigid body inside the frame and how we can describe it. Position in a coordinate. So let's say we have a coordinate system, a two-dimensional planar one, and here we call it A, and this is x of A and y of A. And let's say we have a point which is point P, and how we can define the position of this point in this reference frame. We need a vector that connects the origin to this point. Apologies for my shaky hands. Okay, so this time I try to make it straight. Okay, from origin to this point. Okay, almost. Still I'm not satisfied. So let's try one more time. Okay, I think you should accept it now. So this is a vector. It's pointing toward this point P, and also it has the coordinates can be defined by projecting this vector P on the x and y axis of the reference frame. Okay, so what we do, we make a projection first from this side. Imagine you have some kind of light shining from let's say from this side here. No, not this side. From this side here. From this side a light is shining, and then you will see a shadow from here to here, which is equivalent to this, your red line. And similarly, if you shine a light from top to bottom, you will see a shadow from here to here, a shadow of this vector P vector. And so this is equivalent to this dotted red line. So these are the x and y components of these points. We call it Px and Py. So it means that the position of this position of point P can be defined as, so we call it like P position of point P, and in reference frame A is equal to Px and Py. So we make it like this vector form. So similarly, if you have if we are using 3D frame, then this will be equivalent to Px, Py and Pz. So this is how we describe a position of any point or a vector or a rigid body in a planar or a three-dimensional space. Now let's see how we can describe the orientation of any point in the frame or in the coordinate system. Orientation of a rigid body in frame. So in frame means this is a coordinate system we have. So let's say for a two-dimensional example, where we draw a two-dimensional axis, and then we have, let's say, a rigid body, or you can also take a point. So we take it a rigid body here, and let's say this is some kind of rigid body here. And what we are interested in finding the orientation of this rigid body. So the first thing we do is we make our axis, our frame, our coordinate system, and this is the x-axis, this is the y-axis, and let's call this this coordinate of the frame, we call it frame A. Okay, and what we need to do, we need to so this was our reference frame. We need to attach a body fixed frame here with this rigid body. So we can attach another frame here, which is, you can call it frame B, let's say. Okay, and so let's say these are the unit vectors of these frames. So this one is x of B hat. So this is a unit vector, so its value is 1, and then also we have y of B hat. So this frame we call it B, and so similarly we can also, this one we call it A, and this is also unit vector, let's say. So now we have two frames. One is this black colored, this is our reference frame, a reference coordinate system, and then we have a frame B, which is a body fixed frame. So it's attached to the body and it rotates and moves with the body. Wherever the body goes, this rigid body black color, wherever the body moves, this frame is permanently attached to this body, and it will move and rotate and translate with this object. So now we are interested in finding the orientation of this this rigid body, or you can say this frame B, with respect to frame A, because A is our reference frame. So yeah, so how we can do that? Again, we from here, from the origin of frame B, we measure the position in the frame A. So we can, as we have studied in the previous slide, we can do it by making a vector, by joining the origin to this point, and this is a vector we have, and yeah, so let's call this vector as P. Okay, and here we define axis. So the position of this body, this rigid body, we have already seen that the position can be described by this vector. Because it's a two-dimensional, we can call it px and py. So px and py, this will be the position. We have already studied it, and now we are interested in orientation. So the orientation of this body can be described with a positive angle from the x-axis, which is theta. So this is the simplest method of describing our orientation. So now you started to make some resemblance between this, why we are doing it. So you remember, we are interested in finding the position and orientation of our robotic manipulator, of our robotic arm. In the previous lecture, we did that using the geometric methods, by finding the angles and then using different by combining different joints, we finally were able to find the final position and orientation of our end effector. Actually, I think we only calculated the position, and yeah, but now we are interested in learning another method, which is algebraic method for finding the position and orientation of your end effector. So that's why we are doing it. So yeah, so if your robot is somewhere here, the manipulator, so you can easily find its position, which is px. Position will be px, and py, we already did that in the previous slide, and the orientation can be calculated using this angle theta. This is the simplest method, but there is also more, like a better systematic way of describing the orientation, and this is, you can describe it using this so you can call it like xb hat is equal to cos theta xa hat plus sin theta. So this is how you will. So what we are doing is, we are just converting the coordinates of your body fixed frame into your reference frame, which is the frame A. So that's what we are doing it. So you can easily, if you find here the perpendicular and base, you want to interested in finding the perpendicular and base, you can easily get this equation. Again, you have to make projection of this vector xb along your along your reference axis, x-axis, and also y coordinate, and then you will get this equation. And after that you will do the same thing for the y coordinate of your body fixed frame, and then you will get this equation, which is minus sine theta x a hat plus cos theta y a hat. So this is how you convert these two coordinates for your body fixed frame into your reference frame. So this is another way of describing the orientation of your body into your reference frame. Remember, the easiest one was just finding the value of theta. It will give you orientation with respect to positive x-axis of your reference frame. But this one is more systematic, although it's a little bit difficult, but it's more systematic way, and it's also useful for complex transformation. So once we have these two equations, so what we can do is we can easily write them in form of the matrix form. So what we can do, that we can call them, okay, our rotation matrix, which is R. So R is equal to this, and if you put values from here, and you will get this here, you will get something like this: cos sine theta minus sine theta, and sine theta cosine theta. So this you will get this rotation matrix out of these two equations from above. So here you can see that this is cosine theta, this is minus sine theta, and then you have sine theta and cosine theta. You just have to place the values of this x, b, and yb. Sorry, here I made a mistake. It's y, it's not x. So yeah, so this is xb. When you put here xb, you get cosine and sine, and when you place here yb, you get minus sine and cosine theta. So this is your rotation matrix, and it is used to transform your, it is used to find the orientation of your body, or of the frame, or the body frame, with respect to your reference frame. Okay, and then it can also be used for further many applications, and we shall see them in upcoming slides. Okay, so now we have a rotation matrix. We also see that how we can drive rotation matrix from other examples, or how we can apply rotation matrix for different things. The first thing is rotating a vector. So let's imagine we have a two-dimensional coordinate system, and we have x, and we have and let's call it this one y. Now let's imagine we have a vector here, and this vector goes from origin to some point here. Okay, so to calculate the x and y components, let's see, here we have x component, and this component here is x small, and here we have y. And this angle we have theta. Let's say the length of the vector is r. So now what will happen if we rotate this vector? If we rotate it with some angle, let's say phi, the angle is phi. So after rotation, this will look like something like this. Now this angle is theta plus phi. Now here this is a new coordinate y dash, and this is the new x coordinate x dash, and now we have this r. So the r will remain same. Okay, now we want to calculate the value of the new coordinate, which is x bar, x dash or y dash. So how can we do that? We can do that using simple equations of, we can say that to calculate the new coordinates. So x bar can be calculated by r cosine of theta plus phi, which is equivalent to, we have r cosine of theta and cosine of phi minus r sine of theta and sine of phi. So this can be also written as r cosine of theta and cosine of phi minus r sine of theta and sine of phi. Finally, we can write it as x cosine of phi minus y sine of phi. So because this r cosine of theta, this is equivalent to your x component. If you look at here, so r cosine is equal to your x component, and similarly your r sine of theta is equal to your y component in this right angle triangle. So that's how we calculate the new x coordinate. And similarly we can calculate the new y coordinate, which is equal to r sine of theta plus phi sine of theta cosine of phi plus r cosine of theta sine of phi. This can be written as r sine theta cosine phi plus r cosine theta sine phi. It can be further simplified as r sine theta is equal to y component, and we have now cosine of phi plus x. So r cosine theta is equal to x component, and now we can write here like sine of phi. We can rearrange it and write it like this: phi plus y cosine of phi. So you can see that the new coordinates, they are dependent upon the old coordinates and also the angle phi by which your vector has been rotated. So this new rotation angle, this matters. Theta doesn't matter, only the old coordinates and the rotation angle by which rotation has been done, this matters. So this is how you can calculate the new coordinates. So this equation can be written as the previous equation can be written as, it can be written as in a matrix form like this: x bar and y bar. This is equal to cosine theta minus sine theta, sine theta and cosine theta. With x and y. So from here, x bar is, you see that it's a product of x with cos, sorry, not theta, it's here phi. So yeah, so x dash is the product of x cosine phi and minus sine phi. So cosine phi minus sine phi. And similarly y dash is the product of x sine phi and y cosine phi. Sine phi and cosine phi. So after multiplication of this matrix, you will get the same equation as you get in the previous. So this above equation is not equation, I would say matrix. So this above matrix is known as rotation matrix. You can say R is equal to cosine phi sine phi minus sine phi and cosine phi. So this is your rotation matrix. The angle can be, it can be any symbol, it can be theta. So actually it matters that how much your vector has been rotated. Okay, now we shall see how we can rotate a coordinate frame. So let's imagine we have a coordinate frame here, and so this is the original coordinate frame. X component, and then we have Y component here. And now let's say we have, after rotation, so we get a new coordinate frame which is like this. So this was the old one here, X and Y. And after rotation we get like this one. So this we call X dash and Y dash. So we have rotated this coordinate frame with the angle, let's call it theta. So it means that the X component will be, X-axis will be rotated by angle theta, and same is true for your Y coordinate. So yeah, so how can we now calculate these? How can we represent this new rotation or orientation of this frame? We know that this axis here, this is equivalent to sine theta, and this coordinate here is equivalent to cosine theta. Okay, and or you can say here like this one, this cosine of theta. And same is true for this coordinate here. If you project this one, this is equal to minus sine theta, and if you project this one here on x-axis, then this is equal to cosine theta. Okay, now we are interested in finding the new rotated coordinates. Okay, how much they are rotated. How can we do that? So one method is using the rotation matrix. We know that the new coordinates the new rotated coordinates, actually it should be the new rotated coordinates can be found using rotation matrix. So we have already know this formula. We know that when we rotate our coordinate, we have learned in the previous slide here, when we rotate a vector, So we can use this rotation matrix to find the new coordinates. Okay, so here if you see we can consider this our rotated frame as two vectors. One is x dash and second is this y dash. So now we have two different vectors. So it means we can use this formula here to find their x and y components. So it means that we can find the cosine theta, sine theta, and then minus sine theta and cosine theta. So this is a rotation matrix, and now what we multiply it with the x and y. So for the x component, this x value is 1 and 0. This is because if you see here the x-axis is only located on the x component is only located along x-axis. So when you put here will be 1 and here will be 0 because x coordinate don't have any y component. Okay, so it will be 1 and 0. So that's what we did here, 1 and 0. And if you multiply this, we get something like cosine theta and sine theta. And similarly, we can find the y component, cosine theta, sine theta, minus sine theta, cosine theta. And this time when we multiply with xy, so for y component x will be 0 and y will be 1. So from here, so this y component is only along y-axis, it has no x component. So that's why for this we have here 0 and here 1. So after multiplication, what we get? We get minus sine theta and cosine theta. So this is how we can find the new coordinates, rotated coordinates. You see that the rotation matrix is pretty useful. It can be used to find the coordinates of the newly rotated vector. It can be used to find the coordinates of the newly rotated frame also. So we know that what are the coordinates of the rotated frame, which is rotated by angle theta. Okay, now let's see how we can transform a coordinate from one frame to another frame. Transform a vector from one coordinate frame to another. Frame. So let's say here we have a vector in a frame, and the frame is called B. X of B, Y of B, so this frame is B. And here we have a vector pointing towards the point P of length R, and so its y component is yb and x component is xb. So what will happen? So what we want to do is, here we want to represent this vector R in another frame. Okay, the angle here is, this angle is phi. So now let's make this one again, but this time we make it, this axis a little bit tilted. So here we have our vector so this is point P, this is vector R, and this is the angle phi we have, and this was the y component of this axis, yb, and this was xb. So what I did, I represented same thing here, but this time the whole axis is, its orientation is changed. Okay, but the orientation of vector in this frame, this is same. The angle phi is same as we have here. So now let's say that we know that this vector P or R, it is in this B frame B, it has, its orientation is phi. And what will be its orientation in another frame? Let's say we have a frame and we call it A, a new frame. So what will be the value of this vector R in this new frame, which is an A frame? So what we do, we just project this vector on our new axis, and then we have its x and y component. So this will be x of A, and this will be y of A. It's x and y components. And this angle here, this angle is theta. So let's see how we can calculate the new coordinates, these ya and xa. Okay, so to calculate the effect of this vector in a new frame A, so we can use same method for that we used previously for rotation of a vector. If you remember from previous slide, so here we did to calculate the new rotating a vector. You remember here we rotated the vector in the same frame, so we can apply this same method for rotating a vector in the another frame also. So let's see how we can do that. Okay, so we have here xa is equal to r cosine theta plus phi. If you see this triangle here, this is cosine of theta and phi for this right angle triangle, and this can also be written as r cosine phi and cosine theta minus r sine phi sine theta, and finally this can be represented as xb cosine theta minus yb sine theta. Similarly, we can find the y component in the new coordinate, which is r sine phi plus theta is equal to r sine phi cosine theta plus r cosine phi and sine theta, and finally it can be reduced to xb sine theta plus yb cosine theta. So if you want to let's write it in matrix form. So we can write it like xa y of a is equal to, we have cosine theta minus sine theta, we have sine theta and cosine theta, xb y of b. So again you see this matrix here, this is a rotation matrix. So it means that just simply multiplying the x and y components of the previous frame with the rotation matrix, we can get its components in the new frame. This is another use of the rotation matrix. Okay, so now next we see that how we can rotate and translate a coordinate frame. Previously we have seen that we did a lot of rotations of the frame, we did rotations of the vector, but now what we do, we rotating and translating. A coordinate frame. So as it's clear from the name, along with rotation, it will also have linear motion. The linear motion of the frame. So why we need that? Again, because of robotics, we know that it's normal that the robot has multiple joints, and so if we attach, so let's say this here we have a robotic manipulator, and it looks like something like this. Then we have a link here, one link here, and finally here. So, and this is, let's say, the end effector or gripper we have here. So you see that here we have different kind of frames. One frame is here, this is, let's say, frame A. And then we have a second frame here. Let's make it like frame B. And then we have a third frame here. You can make it like this. Frame C. And these are the X, Y coordinates. XB, YB, YC, XC. So you see that these frames, they are rotated and also translated with respect to, if you see the frame A as a reference frame, okay, and if you want to compare it with your B frame, so clearly B frame is translated. It's not rotated, it's only translated. So there is a translation here. It has a fixed distance from frame A, but the angles are, there is no angle orientation. So if you see frame C with respect to frame B, so this frame is rotated and also translated. So it is at a distance away from C, and also the X and Y axes are not parallel, so it means there is rotation. So to find the kinematics, the position of your end effector using algebraic method, you have to do these transformations, conversions of one frame to another frame to finally find the position and orientation of your end effector with respect to frame A. So that's why we are doing it. So let's see how we can do that, how we can finally do the calculation for this. So let's say we have two frames. Here we have frame 1. So this is, we have frame 1. Let's make with some darker color. So here, this is frame 1, frame A. And then we have another frame which is translated and also rotated with respect to frame A, and we call it frame B. And this is how it looks like. So this is frame B. Here we have B, and here we have so let's say what we are interested in, we have a vector, we have a point P, and this point P is present somewhere here. Let's say this is point P we have, and then we have here a vector, a line that connects this point. That was pretty straight. So this vector in your frame A, then this is a vector in your frame B. Okay, so, and this is the origin of frame A. We call it frame A. And this is frame B here. And its distance, this is delta y, the distance between frame A origin and frame B origin. And here we have delta x. So yeah. Okay, so what we want to find here is we are interested in finding the coordinates of this point P in your frame A. Frame A should be also, I think, let's write it in also same color. What we are interested in, we want to find the position of this point P position in your frame A, the x and y components. So this is, you can call it XA, no sorry, YA. Come on. This is your XA. So we want to find its the position in your frame A. So if you remember previously when we did the kinematic solution, we used some kind of trigonometric rules like converting angles, and so this time we use simply rotation and translation matrices that we learned in the previous slides. So what we need to do here, the first thing we do is we try to find the rotation. For example, what we do, we make a, so we imagine that this frame A is located here at the origin of frame B, okay? And then what we do here, and this is, let's say we call it frame C. and frame C is an intermediate frame. Frame C is our intermediate frame, and frame B, sorry, not green, the red color. This is frame B. Frame B is the rotated and translated frame. So here what we did, if you see that we have already this frame B, red color, and what we did, we made a same frame as we have frame A with the blue color here, and its origin is same as with frame B. So the advantage of this is, first we try to find out what is the rotation here, how much frame B is rotated with respect to frame C. Frame C is an intermediate, or you can say a temporary frame. So here we try to find the angle. So let's say this angle here is, this angle is theta. So it means the frame B is rotated theta angle with respect to frame C, and the angle between the frame B and your vector is phi. Okay, so now we have these all quantities, and now first we try to find the rotation, that what is the effect of rotation of frame B with respect to frame C. And you can use same principle as we did here, rotating a frame, rotating a coordinate frame. So you remember here we used so this was x bar, y bar was a rotated frame, and then we have x and y was the original frame, and theta was the angle. And what we did, we used simply just we multiplied the rotation matrix to get the final rotated coordinates. So same we do here. So here also we have the blue frame, which is not rotated, which is similar to frame A, but this is a temporary frame. And we have a rotated frame, which is the red color frame B, and we try to find the effect of rotation. To find the coordinates. Of rotated no, sorry, not rotated, it's intermediate frame. Of intermediate frame which is C. So what we do here, we just use the rotation matrix. And how we can write it here, we can write like this, like position of with respect to frame C, this is equal to, we have x of C and y of C, and this can be obtained by multiplying the rotation matrix with the coordinates of your rotated frame, x, b, y, b. So here what we did here, look, we wanted to find the coordinates of your intermediate frame C, which is not rotated, this blue color one. And So, and we have this is our rotated frame, which is xb and yb. So what we did, we multiplied xb, yb with our rotation matrix to get the rotated coordinates in your intermediate frame. Okay, and to find the coordinates of intermediate frame, so this is for rotation. So this is for rotation, and if you want to find translation, then what you need to do, you need to convert this frame C into frame A. So it's clear that if you add the coordinates of your intermediate frame, which is the frame C, to this delta y and delta x, you will get frame A. Okay, so the coordinates of frame C plus this delta y delta x is equal to the x and y components of frame A. So we can write it here to get the coordinates in the reference frame. Frame A. We can use translation, and this is how we can do that. To represent a point in your frame A, what you need to do is to add the coordinates of frame C plus delta x and delta y. So this is how you get the translation. You can translate your frame C into frame A. So see, finally what we did here, we wanted to have the coordinates, these coordinates xb, yb in frame A. We want to represent them in frame A. So first we multiplied it with our rotation matrix, and we get the intermediate its coordinates in the intermediate frame C, and then in this intermediate frame C we added the delta x and delta y to finally get the coordinates of your point P in the reference frame A. Okay, so now let's see what are the homogeneous transforms. So what we do here in homogeneous transforms, we use to combine rotation and translation in one operator. So this is an advantage of using homogeneous transforms. So previously you see that we were doing the things separately. First we did rotation by multiplying with the rotation matrix, and then we did translation by addition. So in homogeneous transforms we try to do both these things in one step. A two-dimensional vector giving the coordinates of a point is extended with a third element that has fixed value of 1. So previously we were doing like x, y, but this time when you define a vector, it will look like this: x, y, and 1. So this is the two-dimensional vector. It will look like this. And then your rotation matrix. Rotation matrix will look like something like this. You have cosine theta, then minus sine theta, and then you have sine theta, cosine theta, and here you have 0, 0, 1, 0, 0, and this is how your rotation matrix will look like for homogeneous transforms. Why we are adding 1 here? Because if you see the previous vectors, position vectors here, x, y, only x, y were there. But here we have included a third row in this vector. And here also you see that previously it was only cosine theta, minus sine theta, sine theta, and cosine theta. But here we have added one more row and one more column. So this is because to simplify your calculations, and also you see it looks like also rotation matrix looks like symmetric also. And yeah, so in short, it simplifies your calculations, and also when later you have to multiply it with some other matrices, so if it's symmetric, then it's easier. So yeah, so these are the advantages of using homogeneous transforms. In homogeneous transform, we do rotation and translation simultaneously, and we add one row and one column to the rotation matrix. Okay, how about translation? So since there is not much space here, so I will write here translation, something like here. So if you want to translate translation matrix, so this is, previously if you remember, it looks like something addition of two vectors, but this time we use a matrix that can only be multiplied. So it can be written as 1, 0, delta x, and then you have 0, 0, 1, 0, 1, delta y. So now when you multiply this translation matrix with your any coordinates, it will give you the same result. It will give you translation effect. Okay, so you multiply this translation matrix with some kind of vector, and your coordinates will be translated. If you multiply your coordinates with this rotation matrix, and then your coordinates will be rotated. So combining these two in a single equation, this will give us homogeneous transforms, and we continue this thing in the next slide also. Still we are doing homogeneous transforms. Okay, take the example take the previous case where we have to rotate and translate the coordinate frame. So I'm talking about this one here. This one here. So we did here translation and rotation. So let's take same example, but this time we are using homogeneous transforms. So using homogeneous transforms, we can find the intermediate coordinates, which is x of c, y of c, and then 1 is equal to, how we can get the intermediate coordinates? By multiplying it with the rotation matrix. 0 minus sine theta cosine theta 0, then we have 0, 0, 1. We multiply these coordinates of rotated frame, and 1 to get your intermediate coordinates, and then so once we get the rotation, we will get the, now let's write here rotation. So this was for rotation, and for translation, so how we get the translation effect, as we studied in here, you just have to multiply it with the translation matrix here. So you want to find finally your position in the reference frame. So what you need to do, you need to multiply your translation matrix with your intermediate coordinates. So you see that the resemblance, what's going on here. So here for rotation, we multiplied the coordinates of your rotated frame with the rotation matrix, as we did here. You remember, we multiplied the coordinates of the rotated frame with the rotation matrix. But here the difference is that only we have this third row in the matrix. And for translation, we multiplied the coordinates of your intermediate frame with the translation matrix. But here we did some addition of two vectors. So now let's combine these two and let's see what we get here. So it means that if we multiply these two quantities, for example, put the value of xc, yc, and 1, this vector here, what we'll get here, we get something like this. So we'll get something like this, x of a, y of a, and 1. So here we have your translation matrix, which is 1 0 1 0 delta x, then you have 0 1 delta y, and 0 0 1, and you multiply it with your rotation matrix, which is cosine theta minus sine theta, and then you have sine theta cosine theta. Here you have 0 0 1 0 0. So when you multiply these two matrices, what you get something like cosine theta minus sine theta and delta x, and you have sine theta cosine theta and delta y, and you have 0 0 1. A little bit correction here, since we put the value here, we forgot to put the value of this here, xb, yb, and 1. So we need to put it here too. This says xb, yb, and 1, and similarly you have to put it here also, xb, yb, 1. So here you see that to transform these rotated and translated coordinates into your reference frame, which is A, you just need to multiply it with this matrix, which is a homogeneous transform matrix that can rotate and translate both at the same time. So what you need to do, you just need to multiply this matrix with any of your the frame that you want to transform, and then you get the rotated and translated frames in your reference frame. So this is the advantage of using the homogeneous transforms. And yeah, so if you have any questions, you are free to ask. You can contact me by email, and we shall end our lecture here. Thank you very much for listening. Bye.